Welcome to Honors Precalculus. In this first session of Chapter 1, we will explore lines in the plane and the concept of functions. Today, we'll nail down the important ideas of slope, line equations, and what defines a function, essential tools that will support your learning in the chapters to come. Today, we will cover two main sections. In Section 1.1, we will learn about the slope of a line and its four cases, including point slope, slope-intercept, and general forms. We will also discuss parallel and perpendicular lines. Then, in Section 1.2, we will dive into functions, exploring what a function is and isn't, function notation and evaluation, domain and range, and the difference quotient. Let's get started. Let's begin with the slope of a line. The slope is defined as the change in the y-coordinates divided by the change in the x-coordinates for 2 points on the line. Specifically, the slope is calculated as the difference in y-coordinates divided by the difference in x-coordinates, as long as the x-coordinates are not equal. Slope measures the rate of change, often described as rise over run. There are different types of slope to be aware of. If the slope is greater than 0, the line rises from left to right. If the slope is less than 0, the line falls from left to right. A slope of 0 indicates a horizontal line, while an undefined slope corresponds to a vertical line. It's important to remember that a vertical line has no slope, which is different from having a slope of 0. Now, let's find the slope of some lines through given points. For the points 2, 3, and 5, 9, we calculate the slope as the difference in y-coordinates, which is 9 minus 3, divided by the difference in x-coordinates, which is 5 minus 2. This gives us a slope of 2. For the points -1, 4, and 3, 4, the slope is 0 because the y-coordinates are the same. Finally, for the points 6, -2, and 6, 7, the slope is undefined because the x-coordinates are the same. Remember, vertical lines have undefined slopes. In this animation, you'll see how the rise over run triangle changes as we adjust the slope. Watch closely as the triangle morphs to reflect different slopes, illustrating how the rise and run relate to each other. Next, let's discuss the point-slope form of a line. The point-slope equation describes a line with a certain slope passing through a specific point. It is written as the difference in y-coordinates equals the slope times the difference in x-coordinates. This form is especially useful when you know a point on the line and the slope. For example, the line through the point 3, -2, with a slope of 1/2 can be expressed using this formula. Now let's move to the slope-intercept form of a line. This is expressed as y equals mx plus b, where m is the slope and b is the y-intercept. This form is particularly useful for graphing because you can easily see the slope and where the line crosses the y-axis. For instance, if we rewrite the equation 2x minus 3y equals 12 in slope-intercept form, we find that the slope is 2/3 and the y-intercept is -4. The general or standard form of a line is written as ax plus b plus c equals 0, where a, b, and c are integers and a is non-negative. This form has some advantages, such as handling vertical lines and providing nice integer coefficients. You can convert to slope form by calculating the slope as -a over b, provided b is not 0. Now, let's discuss parallel and perpendicular lines. Two distinct non-vertical lines are parallel if they have the same slope. In contrast, two non-vertical lines are perpendicular if the product of their slopes equals -1, meaning they are negative reciprocals of each other. It's interesting to note that a horizontal line and a vertical line are also considered perpendicular, even though the formula doesn't apply in this case. To understand why the product of the slopes of perpendicular lines equals -1, consider rotating the slope triangle by 90 degrees. When you do this, the rise and run swap places, and the sign of the new rise flips, resulting in a negative reciprocal relationship between the slopes. Now it's your turn. Try to find the equation of the line that passes through the point 2, -1, and is parallel to the line given by the equation 2x minus 3y equals 5. Remember to write your answer in slope-intercept form. After you've had a moment to work on it, we'll go through the solution together. Great job on that practice. Now, let's transition to the next section, where we will explore functions. We will move from the concept of lines, which are some of the simplest functions, to a broader understanding of what a function truly is. So what exactly is a function? A function is a rule that assigns each element from one set, known as the domain, to exactly one element in another set, known as the range. The key characteristic of a function is that each input produces exactly one output. Think of it like a vending machine. You press one button and you get one item. If you were to get two items from one button, that would not be a function. In function notation, we write f of x to represent the output of the function f for a given input x. It's important to note that f of x does not mean f times x, it means the value of the function at that input. We can also express this as y equals f of x, meaning y and f of x can be used interchangeably. Let's evaluate a function with an example. If we have the function f of x equals x squared minus 4x plus 1, we can find the output for different inputs. For example, f of 0 equals 1, f of negative 2 equals 13, and f of a plus 1 can be simplified to a squared minus 2a minus 2. Make sure to pay attention to the algebra as we work through these evaluations. Next, we will discuss piecewise defined functions. A piecewise function is defined by different formulas for different parts of its domain. For example, one piece could be 2x plus 1 for values of x less than 0, and another piece could be x squared for values of x greater than or equal to 0. When evaluating these functions, always check which piece the input belongs to before performing the calculation. In this animation, you'll see how the piecewise function is graphed. Each piece is drawn on its own interval, so pay attention to the open versus closed dots at the boundaries. The linear piece applies for values less than 0, while the quadratic piece applies for values greater than or equal to 0. Now let's talk about the domain of a function. The natural domain is the largest set of real inputs for which the function is defined. There are some restrictions to keep in mind, such as avoiding division by 0, ensuring even roots of negatives are excluded, and requiring log arguments to be greater than 0. These restrictions can help you determine the valid inputs for a function. Let's find the domain of a few functions. For the function f of x equals 1 over x squared minus 9, we find that x cannot equal positive or negative 3. Therefore, the domain is all real numbers except for those 2 points. For g of x equals the square root of 5 minus x, the domain is all values less than or equal to 5. Lastly, for h of x equals the square root of x plus 2 over x minus 1, we need to ensure x is greater than or equal to negative 2 and not equal to 1. In this visual representation, you will see the domain and range of a function. The domain corresponds to the projection onto the x-axis, while the range corresponds to the projection onto the y-axis. Watch as the highlighted regions change as the curve shifts. Now let's introduce the difference quotient. The difference quotient is defined for a function and a non-zero value h as the difference in function values at x plus h and x divided by h. This quotient measures the average rate of change of the function over the interval from x to x plus h. In calculus, you'll take h to approach 0 to find the instantaneous rate of change, known as the derivative. As we observe the secant line and the difference quotient, you'll see that as h approaches 0, the secant line gets closer to the tangent line. The secant line connects 2 points on the curve, and as h shrinks, the slope of the secant line updates, providing a better approximation of the tangent line. Let's work through an example of finding the difference quotient for the function f of x equals x squared minus 3x. First, we calculate f of x plus h, which expands to x squared plus 2xh plus h squared minus 3x minus 3h. Then we find the difference f of x plus h minus f of x, which simplifies to 2xh plus h squared minus 3h. Finally, we divide by h, leading us to the simplified difference quotient of 2x plus h minus 3. Now it's your turn to practice. First, find the domain of the function f of x equals the square root of x over x minus 4. Next, for the function g of x equals 2x squared plus x, find and simplify the difference quotient. After you've worked on these problems, we'll go over the answers together. To summarize today's session, we covered several key concepts. In Section 1.1, we learned about slope, including its calculation, and different forms of line equations such as point slope, slope-intercept, and general form. We also discussed parallel and perpendicular lines. In Section 1.2, we defined functions, explored function notation, evaluated functions, and examined domain restrictions. Lastly, we introduced the difference quotient. Great work today, and I look forward to our next session where we will explore transformations of functions and combinations of functions.